Sanjeev. Okay. So yeah, so I'm going to present joint work with Grant Rotzkopf as a postdoc, Eric Mandenaiden, my colleague, and then two of my PhD students, Sami Jelassi and Zheng Dao, who I think is sitting in the audience. So yeah, so I'm going to talk about something maybe less modern than Jan. I'm going to just focus really on supervised learning, like the old-fashioned, good old-fashioned setup that I'm going to just recall very briefly here. So to get the notation right, so here the problem is should be known for everyone. We have some data distribution in a high-dimensional space, and in this data distribution, I'm observing a target function f star that I want to learn. And so the problem is really just to figure out this function f star by observing it valuing some points. And so I'm going to try to approximate this unknown function with some model. This is again should be very classic. And so I have in this talk I'm just going to really be focusing on very simple way to measure error, which is just pure classic regression, right? So think about the objective that we want to minimize is some regression like loss with respect to some data distribution. And I'm not going to be able, of course, to minimize this objective directly. I can only have a proxy that is the empirical version of this loss with respect to the data distribution. And so again, with something very classic, so what do we do in terms of what can the algorithm do? So the algorithm looks in my hypothesis class, and if I have access to some notion of complexity, right, that I'm going to mostly specify later in the talk, but think about this some kind of like norm, like how complex is my hypothesis. What the algorithm can do is solve this program, right? Basically find me a hypothesis I've had such that its empirical risk is as close as possible from the best I could do from a given level of complexity. And so what we learned more than 10 years ago by this very nice paper by Léon, who is actually in the room, and Olivier Bousquet, is that in machine learning, we also have a fundamental theorem, right? Is that essentially the population risk, like how well is this function that I've solved, that I got from this program, the error can be decomposed into basically three different sources of error. One that is basically measuring approximation, so how good have I been at designing hypothesis classes that capture interesting functions with low complexity? So that's the first term. The second one that basically rewards me by being able to actually measure uniform deviation, and this is we had a very nice talk yesterday by Denroy that basically really focused on this kind of statistical error. And then of course one should not underestimate the optimization error, right? The ability to actually find such solutions. Right? And it was very nicely captured by this very nice paper by Léon and Olivier. And so the challenges that I see here still like lurking in the supervised learning is really, how can we think about this problem in all generality, right? So first one is how can actually we understand, can we understand how to solve this problem? In particular, when we instantiate these questions when the input data lives in a high-dimensional space, right? So how can we find functional spaces that are robust against the course of dimensionality? And then, of course, we need to be able to develop techniques develop statistical techniques to bound this generalization error. And then, last but not least, we need to be able to find solutions of this problem, right? So in a sense, the reason why, as Sanjeev was mentioning yesterday, there's so much interest and so much richness, in my opinion, in understanding the theory is that one needs to be able to, in a sense, make progress in all these three directions at the same time. And so why do I think that this problem, in a sense, is still like far from being solved, is that if you look at the classical notions of functions that we might want to use as our hypothesis class, like classical functional spaces, really do not play well in this framework, right? And what do I mean by that? So if I look at the functions, if I look at notions of regularity that are very weak, for example, just assuming that the functions I need to learn, they are just locally regular, like let's say I'm just looking for Lipschitz functions, what we know from these classic results by Ulrich, von Luxburg, and Olivier is that the number of samples I need, the sample complexity that I need to identify a function f star, even if it has Lipschitz constant 1, the number of samples I need is exponential in the dimension, right? So this space is too large, right? I need too many samples to find functions there. And if we go in the other direction, if we go for more like classical functional spaces of regularity, that, for example, like Sobolev, right, where you ask that the function has derivatives, and all derivatives up to a certain order, they are integrable. So if I look at these kind of spaces, I also see that the minimax rate of approximation is also cursed unless the number of derivatives that I ask is of the order of the dimension, right? So if you think about images, right, they have, I don't know, 2 million pixels, right? So you would only be, your framework would only accommodate functions that can be derivated 1 million times, right? Which is not a very appealing functional space. And so the question, in a sense, that we are framing this talk is which functions can we, can be provably learned in the high-dimensional regime? And then, of course, one would like to make this question a bit more specific to, things that make it closer and closer to algorithms. So in particular, we'd like to say which functions can be learned with neural networks and using a gradient descent algorithm. And then, obviously, following this program, we would like to, make it more and more closer to the reality by maybe asking like particular questions about the architecture of the neural networks, and even like involving, as Sanjeev was saying, that maybe the signal processing aspect, like the geometry of the domain. So of course today we are not going to solve all these questions. We are just mostly going to be focusing on the first two. And so in today's talk, I'm really going to, I am going to argue that even if you look at the simplest possible neural network architecture, like just a single hidden layer, we are going to argue that there are still mysterious questions, right? It's not, we haven't understood everything that is to know about this model, and I'm going to try to justify that claim. And so what we are going to describe is that with an appropriate scaling, we can understand optimization and generalization through the ideas of optimal transport, and we are going to describe how to actually understand how can we learn using partial differential equations. And in a sense, one of the key elements that is going to be central to our story is, again, this idea that actually Jan also referred to in his talk, that there's a key element that allows us to learn in high dimension, that is the sparsity, right? The ability to find good features. And this is something that is captured in this framework. And then we are going to, on this context, we are going to propose a way to actually modify the dynamics by basically using something that is, the technical term is an mallet transport. But if here in the audience there's people that are, like say, that are familiar with optimization theory, this will be just a particular form of mirror descent that actually gives us better guarantees in terms of convergence and has no impact in terms of complexity. And so we're going to describe that. Okay, so that's the setup. This is maybe a dual neural network, but that's what we're going to describe for the rest of the talk. So what is this model? This is a picture, but one can think about this model that I'm gonna try to learn complicated functions as being a sum of simple functions, right? And this in the harmonic analysis literature is called like a rich function, right? So this little function, thinking that is just like a little ridge, right? That is only active in one direction of the space. And so the question is, what can I learn by stacking a bunch of these things together, right? And so you can think about this rich function as being a one neuron. So these neurons, they have output weights that we can call A, and they have input weights and biases, W and D. Okay? And we can collect the parameters of a neuron into one parameter theta that lives in that space. So in that sense, now we are basically isolating three basic quantities that we care about. So the first one is the dimension of the input domain, D. The other one is the number of data points that we are going to have, L. And then the other one is the size of the network, right? In that case, because there's only one layer, the size of the network is just how many neurons I have, like this N. So, and one thing that actually has been very fruitful in the last years, especially to try to understand this question, is really to think about some kind of like envelope, right? Can I basically put all the different neural architectures into the same umbrella that allows me to understand, that I don't want to develop a new theory every time I change the architecture. Right? So in particular, in this context of a single hidden layer, this is very naturally obtained by just replacing the sum by an integral. Right? Basically, what happens if I put more and more neurons to the model? What is the kind of the space of functions that comes up to? So in general, what you end up with is something very familiar, which is trying to write a function using what's like an integral representation that basically tries to write it in terms of this kernel or this this kernel function with respect to some weights, right? And so this, I mean, if you're familiar with a Fourier transform, this really looks very similar to a Fourier transform, right? And in fact, this analogy has been quantified, and not just from, these are like very, in a sense, results that are already like more than 20 years old, where essentially this intuition that as soon as I have some function that has a little bit of regularity, the Fourier transform has nice properties, right? The Fourier transform decays, so it means that I can approximate it with a finite number of frequencies, right? So what these results essentially say is that one can replace the Fourier atoms by more general neurons, right? As long as they are not a polynomial, this result also holds. And so what is the corresponding functional spaces associated with this integral representation? So the first one is that the most natural way to replace the Fourier transform is what's called like a reproducing kernel Hilbert space, where that is constructed as follows. So first I assume that I have a fixed probability measure on my space of input weights, D. And I look at functions f that I can write, again, as an integral representation against like a weight structure that is a square integral, right? So basically here I'm basically giving I'm putting a Hilbertian structure into that space, right? And so as it was very nicely studied and described by this a nice paper by Francis Bach, the Breaking the Curse of Dimensionality, this in fact this space of functions is actually a RKHS. Yes?
Is gamma meant to be mu?
Correct, sorry, good point. Yes. Okay, so if I put a fixed distribution, I have a corresponding kernel, which is basically just averaging my neurons against this probability distribution. And so this is actually an interesting object. Why? Because we can understand many things, right? There's like the Hilbert structure is nice, right? So we can understand very well how to find functions in that space. So this is a classic kernel-rich regression. And we can understand well also like approximation algorithm, right? So in other words, we know how to go from this infinite dimensional Hilbert space. We know how to sample, right? So basically, if we replace this infinite integral by sampling, we understand very well this rate of approximation, right? And I'm just citing here a couple of papers, like this one was very influential by Ali Rahimi and Ben Recht, but there have been many others, and I believe maybe during this workshop we are going to have a little bit more talks along this direction. So what is the problem, or is there a problem? So the argument, my argument is that, yeah, like one possible limitation is that this space of functions, they are cursed. In other words, that the only functions that live in that space, they need to be very smooth, right? The number of derivatives that functions in the space have to have is, again, is order of D, right? Like the higher the dimension, the more derivatives I need to have. And in the particular case where these kernels actually, so this is a kernel that comes from just a single hidden layer, but as also Sanjeev and other talks yesterday described, one can actually generalize these kernels to more general neural network architectures related to what's called this neural tangent kernel. And I believe that there will be more talks during the workshop that basically go into that direction. Okay, so we are going to learn more about these things during this week. Okay, so what is an alternative? So instead of maybe looking for this Hilbert structure, we can instead go for another notion of complexity that allows for feature selection. And this is what Francis in his paper also described as a total variation space, right? And so here, the only thing we're doing is just saying that instead of actually measuring the complexity of my function in terms of an L2 norm, I'm basically measuring the complexity of my function in terms of basically it's the equivalent of an L1 norm, but in the infinite dimensional space, right? So I'm just going to allow for functions that I can write as an integral over neurons, and I just want the total variation of that measure to be finite. So we know by Jensen that this space is bigger than F1, and this is also known as the Baron spaces. And so, of course, the question is, how can we perform approximation and optimization in that space? How can we find low complexity measures in that space? So we are going to now introduce kind of an analogy, like an ansatz, that we are going to really exploit the fact that our architecture is now very simple, just a single hidden layer. So now we are going to write again my function, my model, not as a sum, but as an average. And maybe already people can see why I wrote here this as an average, but it will become clear later. So I write the function as an average, and then again, if I use L2, what we see is that the energy, like basically the empirical laws or the laws of the model, you can actually write it, you can identify basically two major terms. One that is linear with respect to the particles, and one that is measuring interactions between particles, right? So basically now I'm doing this ansatz where a neuron, I just think it as a particle in some space of parameters, right? In the original space of parameters, right? And so now two neurons are going to interact through basically just this dot product, this kernel. And these neurons are going to be subject to what in physics one could associate with some external field, right? There's a force in that domain that basically pushes, that basically moves things around. And in the dynamics are also measured in terms of this interaction curve, right? And this is actually a Hamiltonian system of particles. And so here, just again to try to connect it with other works that study also these single hidden layer architectures when the number of neurons grows, this scaling here that I wrote is very suggestive, right? So this is very different from the other scalings that are going to be described, where instead of scaling with 1 over n, you scale with 1 over square root of n, you get a completely different picture, right? And this picture is going to be described, I guess, by other talks, and it was also mentioned yesterday by Sanjeev. Okay, so now we can again simplify things a little bit. So let's get rid of discrete learning rates. Let's go to continuous time. And again, this we learned yesterday that one should be careful, but allow me to do that step. So if I look at this velocity that I have in every particle, now I can actually you can really see this in physics interpretation as a Lagrangian system, right? So basically I have a system of coordinates where I follow every particle, how it moves, right? This is a Lagrangian view of things, right? So now I can basically change the perspective and take what's called in physics a Eulerian perspective, right? So rather than basically think that my object are the particles, now what if my object is now the density, right? So basically I'm just going to basically lift the problem, right? Instead of basically thinking that what I need to understand is the position of the neurons, I'm now just going to think in terms of the measure, right? So basically, what is the probability to find a neuron at every possible location in my permitted space, right? So I can actually compute this, measure this with an empirical measure that is basically just tracking where the particles are. And so if I just rewrite everything in terms of this object, now what we see is that now our function is linear with respect to this measure. And so in a sense, because we have changed we have lifted the problem into a higher space, now we get something in return, right? And what we get in return is that now the problem has a very suggestive form in terms of it's something that basically is a convex problem with respect to the measure, right? So it's actually quadratic with respect to the measure. And so it's in particular, it's convex in the geometry of linear mixtures, but it's not convex in general because now we have moved in a kind of more exotic space where now the objects are not we are not points in a Euclidean space, we are basically manipulating measures, right? And so one needs to be careful about the convexity statements. So now in the question is that what is the backprop or what is the gradient descent in that space of measures look like? So it turns out that we can now also take the derivative of the loss with respect to the measure, and this is it's essentially a calculus of variations. And now what we end up is with a very classical setup where basically I have a measure, and in this measure I have a velocity field. I have a measure in a domain, and in this domain I have a time-varying velocity field. And so how can I describe the evolution of a measure under a time-varying velocity field? So this is what in physics is called the continuity equation, right? So basically this is just basically an equation that controls the conservation of mass, and the particles basically are going to be pulled apart. They feel a velocity field. And I have to say that this PDE was developed in the context of single hidden neural networks by 4 papers almost at the same time last year. So there were groups in Stanford by Andrea Montanari, a group in Courant with Eric van den Eyden and Grant, another group in France by Francis Bach, and then Justin Sirignano and his colleague Spiro Paulus. So I have to say at this point is that we haven't made any approximation, right? So this PD is an exact description of the system, even if I have a finite number of particles. Okay, so and why is this useful? In particular, it's useful to as a way to understand this overparameterized regime, right? In the sense that now, if in the system I have more neurons, if I made the neural network wider, the only thing I'm doing here is basically putting more particles into the system, right? And so what we have is in a sense that this description admits what we call a mean field limit, right? In the sense that what this mean field limit, So what this mean field limit tells us is that, in fact, if I just track the evolution of the system with n particles, as n grows, I can actually essentially, in the limit, swap the sampling with the dynamics, right? So in other words, I could pretend that I haven't sampled, right? So basically, instead of sampling particles, I could just pretend that I have some very nice smooth distribution mu bar that I run following exactly the same PD, right? So I can basically first let the dynamics, and then essentially describe the evolution of the system by sampling at the end, right? So in a sense, it's like a, in the limit, I kind of pretend that sampling and learning can be exchanged. In particular, this explains, or this is consistent with this idea that it's not because your neural network becomes wider that suddenly the learning becomes more complicated, right? So here, in a sense, it's very crystal clear that if anything, things should be easier, right, as n grows. But of course, we want to understand how does this PD, when does this PD converge? And if possible, we would like to get something quantitative, right? I mean, can we get some scale of fluctuations in terms of the number of particles and in terms of time, right? That's the question. So the first thing that we do to make, in order to make this progress is that we look at actually one of these recent papers that by Colin Wei and I think Tengyuma and Jason Lee and his co-authors, where they look at the same PD. And so what we did is based on some of basically the treatment that these authors made into this PD, we consider basically a modification of the dynamics where instead of basically following the velocity that I described before, we are now going to modify the flow, like the velocity, with another term that basically says that, if I'm in a position where currently the energy is worse than average, I don't want mass there. I want to remove the mass from that position. And I don't want to wait, that the local transport term brings it out. So what I'm trying to enforce is somehow to teletransport the mass from bad locations to good locations. Okay? So this is actually, you can see that this is what's done by these terms. And because we are doing it in a way where basically what we put here in this term is basically the average of this quantity, what you can verify very quickly is that this evolution preserves mass, right? So it's a legitimate, in a sense, it describes an evolution in the space of probability measures. And so and in fact, one can relate this new change as essentially changing the metric, right? It's like we are doing Wasserstein gradient descent, but the metric in the space of parameters has been changed, right? And this is actually known in the optimal transport literature as this Wasserstein-Fischer-Rao metric, right? Which is basically a hybrid between the original metric, the Wasserstein metric, and something that looks a little bit like KL divergence. Okay, and so the nice thing is that this PD can be discretized, right? So you can actually implement it in a computer using something that is called a birth-death process, where the idea is that if we have neurons in the bad locations, we kill them with a certain rate that depends on how bad they are, and we revive new neurons in new locations. Okay, so what can we say about this modified dynamics, this modified PD? Is that if we have this interaction kernel that is symmetric and positive semi-definite, this is actually by construction true in the case of single hidden layer neural networks. And so if we have these conditions, then the dynamics, basically if we follow this PDE, if we have an initial condition that is sufficiently smooth, basically that has full support, then the stationary points of this PDE have to be global minimizers of the energy, right? And what we get is also a notion of when you are sufficiently close from the solution, what is the rate, right? And the rate that we have here is 1 over t, that again it reflects really this, if you are familiar with the mirror descent, that's what is behind, right? Like this 1 over t is really a reflection of this mirror descent rate. And so, okay, so this term comes with certain advantages with respect to just the pure Wasserstein gradient descent. So now the question, of course, is how can we leverage these nice properties of this PD in the real case, right? When we have a finite number of neurons. So the first thing is that we show is that thanks to an appropriate regularization that we have added into the problem, we can actually discretize the minimizers of this PD, right? In other words, that if I have a minimizer of the energy, I can control this quantity that basically looks like a trace of the kernel by basically the complexity of the original function I'm trying to learn, right? The f star. So in particular, what it means is that now I can leverage this inequality to actually use Monte Carlo approximation, right? Basically what it means is that at every point in the dynamics, I can sample from this measure and get an approximation error that is, in a sense, not cursed, right? Because here is an n, right? It's not n to the 1 over d. And of course, if this function was in f1, then I can learn it efficiently. And the other thing that we have is a generalization bound. So if I have a minimizer of the empirical laws, basically just using the empirical data, and I minimize this objective function, I can control, on average, the distance with respect to f star by basically something that, again, depends on the total variation of the function and has the non-parametric rate of 1 over square root of L. And these terms R1 and R2, they depend only on the particular choice of activation function, right? So if you use ReLU, for example, they are not cursed by the dimension. So they depend on the dimension, but they are not cursed. Yeah. So this suggests that if I want to get, basically by just optimizing the regularization parameter, I can take a regularization parameter that is basically of the order of 1 over square root of L, and I could essentially afford to take a number of particles that, as long as it's basically larger than the number of the square root of the number of data points, I could have an efficient algorithm, right? If I just plug these two results together, that would be the conclusion. But of course, there's something that I kind of put a little bit under the rug, and this, in a sense, why this problem is still like open, is that what I told about sampling is kind of almost a cheat, right? Because what I told about the Monte Carlo bound is that if I first run the dynamics and then I sample, the approximation error is going to be not cursed, like it's going to be 1 over n, right? But remember what I said before is that what we need to control is the other, right? So the only thing that the algorithm can do is first sample and then learn, right? And so this control of fluctuations, that involve dynamics, actually is still something that is ongoing work. And so one of the tools that we are leveraging to understand this control is actually the CLT, like central limit theorem results from like statistical mechanics literature that basically were developed already in the 70s. And so one of the questions, in a sense, one of the open questions here is really whether this Monte Carlo rate allows me to actually swap the order of sampling and dynamics. And I should mention at this point that there's a related recent work by Leonid Shiza, where he actually gets global convergence for the same problem, like TB regularized learning in these infinite dimensional spaces. But again, the rate of basically the rate of convergence, even if the initialization is singular, is caused by the dimensionality, right? So the number of neurons that I would need to certify that I can learn is exponential in the dimension, right? So this, in a sense, this question is still open and actually pretty much interesting. So let me just conclude with what some of the current problems that our group are thinking about and problems that I think are important is, of course, everything I described here involves shallow learning, right? So models that have a single layer, and this still is actually, as I said, there's still a lot of mathematical questions. But of course, one would like to go beyond. And so in particular, we want to understand what are the functions, what are the functional spaces that do not fit into this variation framework. So and this is actually related to what's called like depth separation, right? So can we find interesting functions that have very bad approximation rate even in these variation spaces, like with a single hidden layer, but they can be approximated efficiently with the deeper models. And so we are basically using ideas from dynamical systems to try to find this, to basically study this depth separation. Another one, of course, is that we need to extend, in that case, this mean field formulation for deep architectures, and obviously also trying to introduce more geometric structure, so like making convolutional or graph, for example. We also need to quantify this large deviation principle even for this model. And lastly, another important point that I believe it's important is not to forget is basically what happens beyond this gradient descent that is vanilla, right? So as Sanjeev described, there's a problem whenever going to continuous time gives you like first understanding of what's happening, but it leaves many things under the rug, right? And it's important to understand which things in this context. So with that, I will thank you very much, and here are the references of what I talked about today.
So it's break time, but you can also take questions, so we both can proceed.
Can you give me like some intuition for the L1 S space? Is it sort of like a two-layer network